So today we are very happy to have Ken van Tilburg from the KITP, who will be talking about stellar basins of gravitationally bound particles.
Thank you, Juan. Yeah, so today I will talk about work that was based on this preprint here that came out in June. And the basic idea is that stars, including the sun, can emit particles like axions, not just to infinity, but also into gravitationally bound orbits with important consequences for direct detection here on Earth. And then in work that will appear this week, hopefully, I'm collaborating with a postdoc at Stanford, Robert Lazenby, where we work this out for dark photons as well, not just for axions, which was the case study in my first paper. And there's some qualitative differences with dark photons as well, as I will show at the end of the talk. So I don't have that many slides, so feel free to interrupt me whenever you like. So this is the one-slide executive summary of stellar emission from stars like the sun, as well as more extreme stars. So the first thing you should notice is that stars are very bad at emitting photons for two reasons. One is photons have a short mean-free path, so they can only emit basically from boundary surface layer. And secondly, the surface of the sun, say, is at 6,000 Kelvin and much colder than the 1.5 times 10 to the 7 Kelvin at the core of the sun. And so that makes the sun and any other star a good laboratory for detecting new particles. And this was realized, I believe, in the early 40s by Gamow and collaborators who noticed that, excuse me, neutrinos can give a substantial contribution to the cooling of stars. Not so much the sun, but more extreme stars like neutron stars and white dwarfs, it can be quite significant. So for example, the first 100,000 years of a neutron star's life, the luminosity in neutrinos exceeds that of the thermal radiation from a neutron star's surface. And this is despite the extremely tiny coupling of neutrinos relative to photons.
Sorry to interrupt, but can you tell us what your pictures are? Is this red giant an actual photograph of some kind?
Ah, thank you. The red giant is an actual photograph. It's not Betelgeuse. It's another red giant. I forget the name now. The other ones are artists' depictions, of course.
Thank you.
Yeah, and so the left picture is just a HR diagram, a color magnitude diagram. So maybe for most of you, the right axis and the top axis are relevant. So the right axis is just the luminosity in solar luminosity units. So the sun is just an ordinary main sequence star here with the surface temperature of 6,000 Kelvin. And these other stars that I've plotted here generally give much better constraints on new types of particles like axions, because they're either much hotter or much denser, or both. So for example, the red giant branch is here. So that would be the end stage of a star like our sun. And then once a red giant burns up all of the hydrogen and the helium ignites, then it moves to this horizontal branch star. It becomes a lot bluer, and you can sort of see it here. And that changes the core of the star is no longer degenerate, but it's extremely hot. And then at the end of the sun's life, or a typical main sequence star, it becomes a white dwarf, and it sits down here. So it becomes a lot less luminous, but also much more dense, and is very efficient at Bremsstrahlung of any new particle, including neutrinos and axions, etc. And same goes for neutron stars where you're sensitive to nuclear couplings. Okay, so as I said, these extreme stars are more efficient at emitting these new exotic particles than the sun is, but we can try to detect axions emitted by the sun here on Earth. So say at a detector in Italy. And so many of these dark matter experiments are actually also looking for solar produced particles like solar axions. In addition, they can look for dark matter axions. So say axions are produced in the early universe, they can look for, these detectors can look for absorption of axions that would, say, ionize a xenon atom that then gives a burst of scintillation light. So these are the two populations of axions and other particles. So the relativistic solar axions and the dark matter axions that have been looked for in the past. My idea is that there's a new population of particles, which is basically the same ones as the ones produced in the sun, except a very small fraction of phase space is emitted into bound orbits. So so particles just emitted on threshold are emitted in bound orbits, and they can, it's a very small fraction of the phase space, but they can accumulate for such long times that at presently, the density can be dominated by this bound population instead of this unbound population. So that's the one slide summary. Are there any questions about that? The rest of the talk is details explaining this bound axion population. Okay, feel free to interrupt me. So just to give you some background of what the types of particles and couplings we can look for are. So basically for very light particles, you can classify the leading operators of bosonic particles. So a spin 0 CP even, spin 0 CP odd, or a spin 1 particle. And these are roughly the 10 options you have to leading order in effective field theory. So a scalar can couple to electrons, quarks, photons, and gluons. Likewise for a pseudoscalar with different interaction structure. And for a vector, you can have a kinetically mixed hidden photon, so a massive vector A prime, coupled to the electromagnetic current with some small kinetic mixing parameter epsilon, or you can couple to the anomaly-free B minus L current. And so the case study of my first paper was this axial coupling of a pseudoscalar to electrons. And that would lead to Bremsstrahlung contributions as well as Compton production. You can also look for Primakov production, which is this process, which would then also lead to decay of photons. It turns out that if you want this bound axion population to be relevant, you need this axion coupling to photons to be small. So you need, because there's strong constraints on axion decays to 2 X-rays. So I want an anomaly-free axion with where this coupling is suppressed. So in that case, basically, I want the leading anomaly contribution to be suppressed, but then there's an irreducible coupling of the axion to 2 photons, which is this threshold correction proportional to box A. That is irreducible. And then at the end of the talk, I'll also talk about hidden photons or dark photons for which the same processes occur. Instead of the axion, it's just a massive photon. And now the decay is automatically very slow because it's a 3-body decay and a dimension 9 operator. Okay, so but back to axions. So the Lagrangian is just that of a free scalar field and then an axial coupling to electrons here. And so what I'm plotting here is this axion coupling GAE as a function of axion mass and then the stellar cooling constraints. So from not observing anomalous cooling of red giant stars, you set a bound that's about 4 times 10 to the minus 13 on this axion electron coupling, and it gets weaker at a few tens of keV, which corresponds to the temperature in the core of the red giant. And then likewise for white dwarfs, it's slightly stronger and decouples a bit sooner just because of the lower temperature of the white dwarf. There's some claimed hints that white dwarfs are cooling faster than predicted, but I wouldn't take those too seriously. But this goes to show you that you can constrain these extremely tiny couplings of these new particles. And so this is for extreme stars. For the sun, this would be the spectrum of a massless axion coupled to electrons. So it's mostly this FF contribution, which is this Bremsstrahlung process that I showed. And that gives you a spectrum that's peaked at 1 to 2 keV. And so this is the flux as a function of energy, the differential flux as a function of energy. So this last panel that I showed here was for a massless axion. So what happens if you introduce a mass now? So here I'm just showing you a generic spectrum. It kind of looks like that of Bremsstrahlung, where this is now the differential energy loss rate per unit volume and per unit energy of the axion. Here as a function of energy in units of the temperature of the star. So a massless spectrum would scale like m to the 4th here, just it would be rising because of phase space, and then fall off due to Boltzmann suppression far above the temperature of the star. And if you now introduce a mass, you have some suppression here at low masses, and the minimum energy of the particle is of course the rest mass energy, and still usually most of the emission is into orbits that escape the star. However, some small fraction, basically the area here in this blue band, is emitted into bound orbits. So with kinetic energy less than mv squared over 2, where v is the escape velocity. And I've exaggerated this blue region here tremendously. So on general grounds, if you write this energy loss rate per unit volume for any process, you can, it's usually some integral over all the incoming particles, all the outgoing particles, including the momentum of the axion, as a matrix element, the delta function, etc. So let me just write it, let me factor out the integral over the axion momentum. So by construction, it just looks like this with this other prefactor Q tilde. So to estimate this blue region here is just the part of the matrix element, the part of the phase space integral that goes like mv escape cubed. Whereas for unbound emission, typically the naive dimensional analysis size of this integral is t cubed. So if you do it carefully, you find that the rate of energy density injection, so rho dot at radius r, scales like 1 over r to the 4th. So if you compute what fraction of these bound orbits actually make it to some radius r, so most of it actually doesn't escape the surface of the sun, and only stuff very close to this rightmost blue line will make it to Earth, because it has enough kinetic energy to get there. So it falls off as 1 over r to the 4th times this volume integral of this Q tilde function here, multiplied by the gravitational, the square root of the gravitational potential. So if you compare that to the standard energy density, which is just the total luminosity of the star here, this integral divided by 4 pi r squared, just from Gauss's law. You can see that, so if you take the ratio of these two quantities after some time tau, you find this ratio here. So this is the ratio of the bound axion density divided by this unbound flux, unbound relativistic flux. You find that it scales roughly like this. So as promised, it scales like v escape cubed, this argument here, right? And the detailed calculation shows you that is basically v escape squared at radius r times v escape in the core of the sun parametrically. So that's the small factor. So v escape in the core of the sun is about 10 to the minus 3. V escape here in locally on Earth from the solar potential well is about 10 to the minus 4. So this is a 10 to the minus 11 suppression. However, there's a huge enhancement, which is how long this energy density accumulates over time divided by the radius here. So this tau will be on the orders of millions to potentially billions of years, and r is 8 light minutes, the distance from here to the sun. And so that factor compensates for this one. And so if you, for particles with masses of order the temperature of the sun, the ratio of energy densities goes like tau over 1 million years at 1 AU. And so what is this tau? So this tau is, it's set by the shortest of the reabsorption time in the sun or the decay time of the axion, but both of those are very slow. So basically it's how long it takes for the particle to be ejected from the solar system. And that's the weakest link in my story today. So I don't have a good estimate of that yet. No one does. So all I can do is make a conservative, a fiducial, and an optimistic estimate. So the conservative estimate is just that over 2 chaotic timescales in the solar system, so 2 Lyapunov times, the particle would be ejected. And that timescale is about 10 to the 7 years. It's roughly the mass ratio of the sun over Jupiter's mass squared times an orbital time, which is a year. So that's a really conservative estimate, but even at this point, the local basin energy density would be a factor of 10 higher than the relativistic flux. There's some observational data combined with simulations of near-Earth objects, mostly asteroids or captured comets. And they survive for typically for 10 to the 7 years, but usually at around that time they enter the sun. If you look at the ones that, and of course falling into the sun is not important for axions. So if you look at the rate of ejection of these asteroids, that's about 10 to the 8 years. So these are observation of asteroids that are then forward simulated just on a computer. However, the asteroids that we do observe are biased observationally. They're in the ecliptic plane, and several of them have large semi-major axes that that can cross, that causes their orbits to cross Jupiter and therefore lead to ejection. So there's good arguments that the effective lifetime for most of this population that contributes to the Earth's density is actually close to the age of the solar system. So close to this optimistic timescale. And to give further evidence that the lifetime is long, so friends of mine, Tim Weiser and his grad students, have done a study where they considered that the solar system formed in a primordial dark matter halo, and seeing how much of that primordial dark matter halo survived the age of the solar system. What they found was that orbits that crossed Jupiter's orbit were ejected quickly, but 31% of the 31% of Earth crossing density that did not cross Jupiter survived the age of the solar system. So this would correspond to roughly a lifetime of the age of the solar system, a 1/e lifetime of the age of the solar system. And the picture here is the surviving phase space. So so Vx is so here up is velocity towards the sun. This is radially away from the sun. The Earth is in a circular orbit with tangential velocity of 30 kilometers per second. And this is again, the Vz here is the velocity out of the ecliptic. So what you see is that orbits with slow velocity to Earth are ejected, but the ones here with high eccentricity, because they have a high radial component, do tend to survive. And then another point is that, so this dashed line is corresponds to the velocity where the orbit would cross Jupiter, because it would have enough kinetic energy to do so. And you see that there's no particles there that survive. Okay, so the baseline is that very conservatively, I can say that tau must be at least 10 to the 7 years, very confidently, and very likely the effective tau will be somewhere a few times 10 to the 9 years. So if you do things carefully, then this is what you get. So here I'm plotting the local Axion energy density at Earth as a function of Axion mass for this coupling here, GAE, that's 3 times 10 to the minus 13. So that is a coupling that's just barely allowed by the white dwarf cooling bound. And what you see here is, let's say, this black dot dashed line. This is the massless Axion flux at this coupling here from this. Yeah, it's mostly Bremsstrahlung for atomic processes, Bremsstrahlung and Compton combined. So at this coupling, you get a local density of 10 to the minus 6 GeV per cubic centimeter. From dark matter, just by fiat, if you assume that the Axion is dark matter, you get about 0.4 GeV per cubic centimeter. Now, the third potential population that I pointed out is this Basin population, and for that you find that the energy density is given by this blue band. And the blue band corresponds to these 3 ranges of tau values. So conservative is 10 to the 7 years, optimistic is the age of the solar system. And you see that for masses close to the temperature of the sun, which is about a keV, the local density is dominated by this non-relativistic component, this Basin component, and not by the relativistic flux. There's also a contribution from Bremsstrahlung in the Earth's core, but that is negligible. Any questions so far?
Could you say again what's the red line?
Oh, so yeah, sorry. So superscript C is Compton, the Compton process, and superscript B is Bremsstrahlung.
Oh, okay, thank you.
The Compton process is a bit harder and is the dominant process at high masses, but it decouples quickly, yeah, from phase space, and also because of there's a hard cutoff around here from the finite plasma frequency of the photon. So it's mostly Bremsstrahlung that dominates.
Okay, thank you.
The gold curve. What I have not yet included here is what's this A here, which is atomic processes. So if you look at this paper, this spectrum computed by Redondo, so for a massless Axion, here you find the dashed curve is the Compton process, the dot dashed curve is the free Bremsstrahlung, But then there's contribution from atomic processes, which are free bound and bound transitions, which lead to these spikes. I've not yet computed all of those. So those would give an added, spiky contribution to this energy density. And it would only be relevant for an axion mass very close to some atomic transition energy.
Okay.
Okay, so that is the physics for a solar axion basin. So the publication of my paper was motivated, at least the timing of it was motivated by recent results by the Xenon 1-ton collaboration. So that experiment and many other experiments like it, like Lux, LZ, and experiments in Japan and China, work on the same principle of a liquid xenon time projection chamber. So the basic idea is that a particle can hit the electrons in the bound electrons in xenon atoms, and the particle can be a relativistic solar axion, a non-relativistic solar axion, or a dark matter axion. So that interaction here could ionize electrons that then produces some scintillation light, which is called S1, picked up by the photomultiplier tubes at the bottom and at the top. And this S1 is instantaneous. And then there's also an electric field, some drift electric field here that causes the electrons to drift upwards into the gaseous xenon, and then the electrons hit the photomultiplier tubes again with the delay indicating the depth and the location on the photomultiplier tubes indicating the radial position. So you have some 3D information in terms of radius and depth. And xenon is self-shielding, so the fiducial volume is this interior here where you're cutting out much of the radioactive background, for example. And here's a plot of the amount of scintillation light S1 and this S2 signal, which is when the electrons hit the PMTs. And these are all of the recorded events. And so based on the S1 and S2, you can reconstruct the energy. So this is 1 kV, 2 kV, 3, 4, 5, etc. And so if you make a 1D histogram of this, this is the events per ton per year per keV as a function of energy of the events. And so they found an excess mostly located between 2 and 3 keV. I'm not going to go into too much detail here. So they considered, so their null hypothesis was their baseline background model. They considered exotic backgrounds or more exotic backgrounds than their null hypothesis, which is a tritium background. So tritiated water mainly. And so that can absorb some of the excess events. Although they expected the tritium abundance after their mainly their purification processes to be much lower by a couple orders of magnitude than what is needed to fit the signal. And they did an additional run of 24 days with an upgraded purification system that with lower statistics, but that seemed to still indicate the events. The Xenon 1-ton collaboration then claimed evidence, or at least indications, of more exotic signals like a solar axion, a massless solar axion coupled to electrons. So the solar axion spectrum as reconstructed in the xenon detector would be this blue curve for the coupling to electrons, the purplish curve for the coupling to photons, and from the nuclear coupling, there's a Mossbauer-like transition in iron 57 that gives a peak at 14 keV. And with tritium and the Axion explanation, the significance of the signal is much reduced. However, it's somewhat misleading to claim evidence, in my opinion, because the couplings that are needed are way in tension with stellar cooling constraints. So if you look at what the actual allowed region is in this 3D parameter space, which is the coupling to electrons, to photons, and the nuclear coupling, it's basically this tiny corner here near zero that is that does not overlap with their best fit region. So effectively, you should imagine the coupling to nucleons to be zero because the bound is about 10 to the minus 8. If you do that and just plot the electron coupling and the photon coupling, the stellar cooling constraint is here. So it's about 3 times 10 to the minus 13 on the electron coupling, and better than 10 to the minus 10 per GeV on the photon coupling. And the best fit xenon region requires much larger couplings. Okay, so it's not a relativistic solar axion. It can be a dark matter axion. So for example, the new search, right, it claimed excess for between 2 and 3 keV, and indeed their limit on a dark matter axion in terms of the electron coupling was weaker than expected here. And so the excess would be best fit by an axion in this region. And that is still, you know, it's a 10 to the minus 4, few times 10 to the minus 14, which is still allowed by stellar cooling. Likewise, dark photon absorption could give a similar signal. There's more exotic dark matter scattering explanations, but they are they require usually multiple particles. Okay, so putting everything together and mostly summarizing all of the processes. So I said there's 3 populations, right? So there's the relativistic axion flux, the solar axion flux, the non-relativistic solar basin, or the dark matter, just the dark matter bath. So as I said before, if you look at coupling versus axion mass, this relativistic solar axion flux cannot account for the excess in xenon because the best fit coupling is about 3 times 10 to the minus 12, which is a factor of 10 above the stellar cooling constraints of red giants. So if you wish, if the best fit coupling is here to explain the excess, then you would predict that red giants would cool 100, and white dwarfs would cool 100 times faster than observed. Or you could turn it around and say that the events xenon 1-ton Cs are 10 to the 4 times too large because the signal goes like coupling to the 4th power in comparison with the stellar cooling constraints. And as the xenon collaboration said, the signal can be explained by a dark matter particle with couplings roughly in this regime. However, you don't need to assume that the axion is dark matter. Just if the axion has a mass of order 2 to 3 keV, then the local density is dominated by this solar basin of axions. And if the lifetime of this basin is long enough, roughly the age of the solar system, then it could be explained by an axion in this mass range. Although it's only just eclipsing the white dwarf and red giant cooling bands. But just as a general point, even if you do not believe the excess that the xenon collaboration sees, my claim is that above a few times above 0.2 or 0.3 keV, the non-relativistic solar basin population actually improves the reach of any liquid xenon experiment to the point where now they're competitive with stellar cooling constraints. And it's plausible that the xenon collaboration or Lux or Panda X will see something, we'll see a solar axion with mass of a few keV in the near future. So this is everything I have on axions. So for the remainder of the talk, I will show you the equivalent plots for a hidden photon. So maybe I'll stop here for a couple of questions, if there are any.
Can you determine the direction in which the axion comes?
So yes and no. That requires detailed simulation, which I plan on doing. But so this is the phase space of dark matter, but it would be axions as well, in heliocentric coordinates, right? So for Earth coordinates, you have to boost by 30 kilometers per second. So the main contribution to the density is very radial orbits. So the basin is injected from the sun and initially on radial orbits, right? And most of the contribution is, so therefore, most of the contribution is just when the orbit reaches its aphelion at 1 AU. So would have very low velocity. So basically the velocity would be in the center of this panel here. That's where it's injected. However, planetary perturbations change the orbits, and it seems very likely that the surviving phase space, even with this different initial condition, would look like this phase space. So there's a slight preference for eccentric, high inclination, and slight retrograde orbits. So that's the prediction. The xenon experiments do not have directional information, unfortunately. So they just can see an event and they're not sensitive where the axion came from. As I'll show you later, some hidden photon experiments are sensitive to direction, so they can determine this. One thing that could, so as I said, so a dark matter absorption is hard to distinguish from a solar basin absorption. They're both non-relativistic particles where the energy absorbed is the rest mass. But the annual modulation signal for a solar basin would be stronger than for dark matter excess. So basically, because the basin density falls off as 1/r⁴, just because Earth is on a slightly eccentric orbit, you would predict on the order of 7% annual modulation for this signal, whereas it's only 1% for dark matter due to gravitational focusing of the sun. So that's the way you would distinguish. It's just the temporal modulation. The direction is not sufficient, unfortunately.
I see. Okay.
All right, then I'll continue with hidden photons. So hidden photons is very much the same, with one major qualitative difference. So here you just have the regular Maxwell Lagrangian plus a new massive photon, A prime with field strength F prime and mass M here. And this is the usual interaction of R photon with the electromagnetic current. But so if you have the small kinetic mixing here with proportional to epsilon, then that basically induces, after a field redefinition, a coupling of A prime to the electromagnetic current suppressed by epsilon. And at very high masses, the same processes that occur for an axion are operative for a hidden photon as well. So for high photon masses, things look very similar. However, for low dark photon masses, so for masses below the plasma frequency inside the sun, basically below 300 electron volts, a new qualitative phenomenon occurs, which is resonant production. So you see at low masses, most of the production is dominated not just by the core, but by one thin shell where the plasma frequency of the plasma frequency in the sun matches the dark photon mass. And another feature is that in the limit of 0 dark photon mass, the dark photon decouples. So you can just do a field redefinition and absorb epsilon in a redefinition of the gauge coupling. So you know physically that at low masses, any effect, including stellar emission or solar emission, should decouple, and that's indeed apparent. So at fixed epsilon, the luminosity into bound orbits for m equals 1 eV is much lower than for 10 to the 3 eV. So that actually means that instead of just being sensitive to keV mass particles, like in the case of the Axion, here there's hope for a much lower mass particle production. Okay, so this is the analogous plot of what the energy density of this basin looks like. So for fixed epsilon of 10 to the minus 16, you get this curve here. So you see it has more features, and that's because of the maximum plasma frequency of 300 electron volts inside the core of the sun. And it also doesn't decouple as quickly. You also see, so this is for fixed epsilon, and if you put epsilon at the current limit, you can actually get densities of order the dark matter density, or close to saturation density, where the occupation number is so high that you actually approach detailed balance with the sun for these bound modes. And so this is what's shown here. So the local occupation number would reach this saturation level. Yeah. So in the end, what this translates to on constraints is that as a function of dark photon mass and this kinetic mixing parameter, so previously you just had the stellar cooling constraints. So the solar cooling constraint was the most sensitive at low masses. So that's this curve here. You see it's most sensitive near the plasma frequency in the solar core, and it decouples at low masses, unlike for the Axion. And then these more extreme stars, because they have higher plasma frequencies and are less well measured, they actually set weaker constraints at low masses, but they set the best constraints at a few keV and tens of keV masses. Then there's the relativistic solar Axion search by Xenon 1 ton, and that recently set a constraint of this solid, this bold gray line here. But the solar basin production, if you reinterpret the dark matter searches by the Xenon 1 ton collaboration and assume this conservative gravitational ejection time, you find a new limit that actually exceeds the current stellar cooling limit in this tiny corner, even with this conservative ejection time. And if you take our new fiducial time based on these simulations by Tim Weiser et al. That show that most of the phase space survives, or an order 1 fraction of the phase space survives the age of the solar system, you find that very likely the actual limit is close to the solid line here. So then you would probe new parameter space between 12 eV, which is the ionization energy of xenon, all the way to 5 keV. And if you interpret it as an excess, it would be this orange parameter space here at 1 and 2 sigma. future experiments can do much better even at low masses. So this curve here, this dashed curve, is the super CDMS Germanian projection on hidden photons. And these are the equivalent dark matter searches. So basically, for example, the super CDMS search for dark matter, if recast as a reach on basin, solar basin dark photons, would be this blue region here. Okay, I think I'll stop here. So basically, I've shown you that the sun can produce KeV scale type particles and that they can be detected by direct detection experiments. And in the future, I'm investigating a few more directions, which is that decays of these particles or conversions around the sun and other compact stars could lead to indirect detection signatures in X-ray observatories or gamma ray observatories. And you can, in principle, apply this this mechanism to any particle. So I've done it for axions coupled to electrons in hidden photons. But you can also apply it to scalars and potentially general axions and potentially also neutrinos and fermion pair production of fermions. And what's definitely left to do is to characterize the orbital dynamics and evolution of this stellar basin carefully. So not just to estimate the gravitational ejection time, to estimate the local expected density, but also consider absorption and saturation of the basin, especially for the hidden photon where production is so efficient, and also to characterize what the statistics of the density are. So what are the fluctuations statistically and in time. And in the future, there's many new direct detection analyses forthcoming. So you heard about the Xenon 1 ton collaboration that published results recently. Xenon N ton is happening soon. The LZ collaboration hopes to start taking data next year as well. And the Chinese and Japanese collaborations are close as well. And for hidden photons especially, there's a lot of activity to develop dark matter experiments with much lower thresholds. And these experiments could also look for this solar basin hidden photon population. Okay, I'll stop here and I'll take questions. Thank you.
Okay, thank you.
Are there any questions?
Well, it's not exactly a question about your talk, but on the Xenon 1 ton, how compelling are background interpretations? Or
yeah, right. So there's some concerns. I don't think I have a slide on this. There's some concerns that it's some unmodeled radioactive background. I'm not the expert on this, and I believe we may have some tuning into the call. But it's a bit worrisome that most of the excess came from the first few months of data taking, when radioactive backgrounds are still in the process of decaying. So that is a little bit of a red flag. So there's some concerns, not just about tritium, but also about one isotope of argon, for example. Yeah, I don't have anything intelligent to say about that. I would not put my money on the excess being new physics, but that's something they will hone in on soon. I do think they did show convincingly, at least to me, that it's not a threshold effect. So of course you may worry that since their threshold, their efficiency drops off very steeply below 1 keV, that it could be some sort of detector effect. And I think that that explanation they excluded using a radon calibration source.
Okay, thank you.
So you said there were some experiments in the future that will be able to detect the direction.
Ah, good. Yeah. So it's in fact experiments that I've worked on in collaboration with Robert actually, and other collaborators. So that's the STAX experiment. So this STAX experiment can, it's a coherent absorption proposal. So basically it's layered dielectrics with alternating dielectric constant. And so in the limit of zero velocity, a dark photon would come in and would be converted into a real interacting photon, exactly perpendicularly to the stack, to the plane of the layers. However, if there's some velocity spread, or depending on the transverse velocity of the hidden photon, transverse to the normal vector of these layered stacks, that would slightly alter the direction of the outgoing photon by an angle relative to normal of V over C. So that would be able to pin down, if this experiment were to see a signal, it would be able to pin down the direction. However, it does get tough because as you see here, this was an experiment designed to look for dark matter couplings of order 10 to the minus 15. But in terms of the sensitivity to a basin hidden photon, it would not be sufficient to exceed this solar axion bound from xenon. So, I mean, this is for a relatively small scale experiment, so it would have to be scaled up to be above this bound. There's other experiments using optical phonons that in principle can be operated in asymmetric materials. So if you have asymmetric crystals, you could have absorption being preferentially along certain crystal axes. So depending on the crystal orientation, you could statistically determine the mean dark matter direction or try to characterize it over time. That does require a significant amount of signal. And yeah, so at low energies, I think there's some hope. For these liquid xenon proposals, I don't know of any feasible proposals doing so.
Mm-hmm. Are there any further questions? Do basins of attractions around other stellar bodies play any role, or?
Yeah, and I think I forgot to mention this, unfortunately. So I just realized. So the idea of gravitationally bound emission was, unbeknownst to me, proposed by Hannestad and Georg Raffelt in 2001. So they considered Kaluza-Klein modes at tens of MeV emitted around in a supernova around a proton neutron star. And so they, I mean, I think their conclusion was negative, that it wasn't a strong constraint. yeah, so that is something I would like to think about soon. So in my work, I assumed the I guess here I assumed the photon coupling to be quite small, so Primakov wouldn't play a role, and the decay of photons wouldn't happen. So if the photon coupling is not suppressed, then I think you can constrain this solar basin from an X-ray line close to the sun. So basically the solar basin, the lifetime would still be longer than the age of the universe, but you would see some X-ray signal from near the sun. And I think that can be looked for. So yeah, but that's work in progress. I don't have numbers for you right now.
Okay, well, great.
And indeed, around a neutron star, the escape velocity can be order 1, right? So then in principle, and for a sufficiently heavy particle, then an order one fraction of the luminosity can be emitted into bound orbits.
Any other questions? Well, if there are no more questions, let's thank Ken again.
Thank you.